Well, welcome back. We're going back into geometry and measurement on our proficiency test topics, and we're going to look at some congruent and similar triangles. Now, first things first, congruent triangles means that you have two or more triangles that are exactly the same shape, exactly the same size. They have the same angle measures, they have the same side lengths as one another in a corresponding manner. Similar triangles, on the other hand, they have the same shape, but they don't have necessarily the same size. Like a similar triangle, one might be kind of like a blow-up or shrink it down from one to another, like an enlargement or a reduction of some type. So similar triangles and similar shapes in general, they have the same shape, but they don't necessarily have the same size. A really good example of that would be circles. Circles all have the same shape, but they can have different length radii, and they can have different sizes. Congruent triangles. In the figure below, as you can see, I've drawn one here. Triangles A, B, G, that's this one. Now notice the correspondence, A, then B, then G. B, C, H, B, C, H. It was A, B, G, B, C, H. A and B go together, B and C go together, G and H go together in the same order. A and B, B and C, G and H. That's a way to show which angles go with which sides go with which. Side AB goes with side BC, side BG goes with side CH, and so on. And one more triangle, HGB, HGB, in the same correspondence, HGB, ABG, and so on. You are asked to find the measure of angle GBH. GBH. That's this angle right here. Well, here's how it goes. If I know that angle, the first two triangles mentioned, ABG, BCH, if I know that A corresponds with B here, then that means this is 62 degrees. And C here, which is 54 degrees, corresponds to B, that would be 54 degrees here. Now, we know that the three angles of a triangle, the measures, add up to 180. So if I add those two together, I get 116. And if I subtract from 180, I get 64. So this angle here is 64. This angle here is 64. Now, I'm trying to find angle GBH. Now, look where that's at. It's the one on the end. The one on the end here, the one on the end here. 64, 64, then this one is 64 degrees. Now there's other ways that you can do this, but that's as good as any. Similar triangles. Now this CSSTP doesn't look like that makes much sense, but it says corresponding sides of similar triangles are proportional. And we've already discussed proportions back in numbers and operations. I have here a couple of triangles. I didn't draw them perfect to scale, but you can see the little triangle here and then the one that contains the little triangle and goes a little bit further out. It says in the diagram below, triangle RST is similar. The symbol right here means is similar to triangle RVW. Now again, these match, these match, these match in a corresponding manner. Now with similar triangles, they have the same angle size, but they don't have the same lengths of sides. You can see that this length and this length here, this length and this length here, this one here and this one here, they're different. There's a smaller triangle, there's a larger triangle. But the sides are proportional. The corresponding sides are proportional to one another, and that's where our advantage is, because it says here, find the length of RW. RW would be from here to here. Well, look what I've got. I'm going to go little to big. What corresponds to RW? Well, RW on the big one corresponds to RT. That's this guy, 7. Then RW, that's the one we don't know. I'm going to go ahead and actually write RW. Now on the other side, I do know all the measures here. So I'm going to go little RS to big RV. Little is 4. Big is 7, because you have to add the 4 and the 3. So now I'm going to cross multiply. I get 4 times RW is equal to 49. I'm going to divide by 4. And I get RW is equal to, looks like 12 1/4, or 12.25. And fortunately, I have that right there. It is answer C. this example here, we have two triangles that are drawn. It says triangle BCD is similar to triangle FED. Again, look at the correspondence. B corresponds to F, C corresponds to E, D corresponds to D. It has to be set up that way when it's written out. What is the measure of angle E? Now we know that although the sides are proportional, corresponding sides are proportional, the corresponding angles are congruent. So what we can do is we can find the one that corresponds to angle E. Angle E is right here. Well, I look at angle E and I see that angle being at least 90 degrees. So I know right off the bat it's not going to be these two. Just on inspection, it's got to be either C or D. I'm guessing it's probably C, but I don't know that for sure until I work the problem out. Now I do know that if I'm trying to match up with angle E, right, angle E, that's the middle letter here. I look at the middle letter here. That's this angle. Well, this one's 35 and this one's 40. I don't know if you can see that very well. That's supposed to be a 40 there. That's 35. So they total 75, and if I subtract that from 180, that means that this angle here would have to be 105 degrees, which means that angle E would have to be 105 degrees. And that's answer C. Now let's talk a little bit about circles. Circles, the formal definition is a set of all coplanar, meaning on the same plane, points, a set distance, which we refer to as the radius, from a fixed point. You've got a center, and then you've got this distance that sweeps around it. Now I free-handed these circles, as you can tell. They look a little bit more egg-shaped than they do a perfect circle, but kind of bear with me here. On this example right here, I have some key ideas marked in here and labeled. A line segment whose endpoints are on the circle is called a chord. The largest chord is the diameter. It goes all the way across the circle through the center. All the way across. The radius is halfway across. It goes from the center to the edge of the circle here. So the diameter is twice as long as the radius. The radius is half the size of the diameter. And this measure right here, where it goes from here, this curve, that's referred to as an arc. There are all sorts of arcs in here. And if an arc is formed from an angle like this, where the vertex is at the center, this is a central angle, then if the arc is drawn, it will have the same measure as the degree measure here of the central angle. And we'll talk about that in a minute. The diagram below, now this diagram, not this one, this diagram here below shows a circle with center A. Right there at center A it's supposed to be. Which segment has the same length as segment AF? AF is from here to here, so that's a radius. So I would know that any other radius is going to be the same size because it's a set distance. You know, for the all radii of the same circle are going to be congruent. They're going to have the same length. So I have to find one that matches up with another radius here. Would it be CB? Well, CB goes from here to here. That's a diameter. That's too big. That's twice as big. So it's not that. Could it be GH? Well, you know, they look like they could be the same size, but we don't know enough information about GH to be able to specifically say that, so I'd have to throw this one out. CA. CA goes from here to here. Well, that's a radius. So that radius and that radius and that radius, they're all the same length, so my answer is going to be C. ED, that's down here. Again, it looks like it could be a length that it's about the same size, but we don't know for sure, so it's got to be answer C. Okay, in this example, and again, you know, kind of bear with me, not the greatest circles in the world there. All right, I have circle G. It says in the diagram, points D and F are on circle G. Which expression describes the length, not the measure, the length of the minor arc DF? That's from here to here. Well, all the way around the circle is called circumference, and we're going to go into that in more detail later on. But circumference is found by taking 2 times pi times my radius, which is x. That's the distance all the way around the circle. Since this is 90 degrees and all the way around a circle is 360 degrees, this is 1/4 of the circumference all the way around. So I'm going to divide it by 4 to take 1/4 of it. I can simplify. I get pi x all over 2, pi x all over 2. You take the circumference all the way around, 2 times pi times the radius, and what you're going to do then is you're going to divide it by what fraction of the circle your arc is. In this case, since all the way around is 360 degrees, and this is a right angle, 90 degrees, it's 1/4 of the way around. So that's why I divided by 4. and answer A. Circle L down here is shown below. Now this angle right here is the 120-degree angle. That's your central angle there. Then it says, what is the measure of arc KPM? Now KPM, as you can see, is more than halfway around. That's called a major arc. If it's less than halfway around, less than 180 degrees, it's called a minor arc. And in this case, to find the measure, not the length, that would go back to this kind of an idea. What I have to have is I have to know the central angle. Now all the way around, remember, is 360. So if I go 120 this way, that means this part would have to be 240. That's 360 minus 120. So that would be my answer way over here. Now you can kind of tell that was your answer without even having to do the subtraction, because you can see it's more than halfway around. This is less than half, exactly half. Okay, I wanted to mention very quickly a couple ideas on symmetry, reflections, and rotations. Now I have a set of coordinate axes here, and I've drawn what looks like a mustache. And what I've tried to show is that I have symmetry. This shape has symmetry with respect to the y-axis. It's like a reflection of one over the other. And speaking of reflections, a reflection in an axis means that you just flip it over the axis. If I reflect the letter E here, over, and I'm going to make this with a little catch there. If I reflect this over the x-axis, I will get something that looks like that. If I reflect it over the y-axis, I will get something that looks maybe more like this. Not drawn perfectly, but hopefully you get the idea. It's flipped over. Think of a reflection as a flip. A rotation, think of it as a turn or a spin. You're spinning at a certain number of degrees based on spinning it around the origin. So if I said I was going to rotate this shape here, 180 degrees, what that means is I would have to go 180 degrees. So I would end up with something that spun around and would look like this. It's kind of crude, but hopefully you can see it. Rotation means just what you would think. You spin it around. Spins and flips, and then symmetry has to do with like a mirror image. A mirror image of one side to the other side. All right, with all these problems, you've got plenty for practice. Go to www.succeedinmath. And again, check with your math teacher about getting some practice sheets on this, but most of the practice.